Now that we've learned how to describe motion through kinematics, it's time to begin looking at how forces influence motion, which is the study of kinetics. Kinetics is almost entirely predicated on Newton's second law, which says that the force acting on a particle is equal to its mass times its acceleration. So the acceleration of a particle is proportional to the force, the constant of proportionality being the mass. This is also true if the force is varying with time. So if the force changes in time, then the acceleration will change instantaneously along with the force. It's important also to note if there are many forces acting on a particle, then the force of interest is the net force, or the total force. So sometimes you'll see it written as the sum of all forces, just to highlight the fact that it's the net force that we're interested in, equals the mass times the acceleration. Something to note, very important, and that is that the coordinate system from which we measure acceleration is not arbitrary. So this coordinate system must be Newtonian, meaning that it can't be accelerating in any way. So it can't be rotating, changing orientation, or accelerating linearly. It has to be fixed with respect to the stars. We also like to define the linear momentum, L, which is equal to the mass times the velocity. Linear momentum, sometimes we just call it momentum. Later we'll introduce the concept of angular momentum. And when we talk about angular momentum, we almost always say angular momentum in total. If we just say momentum, usually we're talking about the linear momentum. And linear momentum is the mass times velocity. You can write Newton's second law in terms of the momentum. I'll abbreviate Newton's second law as N2, like that. Newton's second law in terms of momentum says that the total force acting on a particle equals the time rate of change of a linear momentum, which is equal to, we can also write that as L dot, which is equal to d dt of mv. Now notice that the mass itself is inside the derivative there, so if the mass is changing with time, we have to account for that. If the mass is constant, then we can simply write it as the total force is equal to L dot, or is equal to m v dot. A case where the mass might be changing, for example, a spaceship that is propelling itself and ejecting burnt fuel out the exhaust. So as it ejects fuel, it's the weight, or the mass of the spaceship itself will change, and we have to account for that. We won't be dealing with those in this class. We'll deal only in cases where the mass is a constant. If the total force is equal to 0, then 0 is equal to the time rate of change of linear momentum. The consequence of this is that the linear momentum has to be equal to a constant. If it's derivative of 0, then it must be equal to a constant. In this situation, we say that momentum is conserved. And remember, that's the case where the total force is equal to 0. Now, it's worth mentioning a little bit about units when dealing with Newton's second law, because the working units are not arbitrary. You have to work in certain units when you're dealing with kinetic relationships. We use two different, conventionally we use two different unit systems, we use the metric system, which is based on the meter for length, the kilogram for mass, not gram but kilogram, and seconds for time. Those are the base units, and then from those base units we derive any other units. We also use US customary units, where the base units are the foot for length, the pound for force, and the second for time. Notice that in the US customary, the base unit is a force, but in the metric system, the base unit is a kilogram. That's an important thing to keep in mind. More on the metric system. Again, meters, kilograms, and seconds. These are all arbitrarily defined. For example, a kilogram is defined as a certain block of platinum of certain dimensions, the mass of that block. The second is defined as the time it takes for a certain material to oscillate a certain number of times at a certain temperature. Things like that. So they're defined in that way. The unit of force in the metric system is the Newton, and it's derived. A Newton is the force required to accelerate 1 kilogram by 1 meter per second squared. That's how a Newton is defined. So it's derived in terms of these arbitrarily defined units. In the US customary system, the defined units, the foot, the pound, and the second, are defined. And, the mass is derived. And we have two masses that we use in US customary units, so two different definitions. The most common is the slug, right? And a slug is defined as the mass that accelerates by 1 foot per second squared when acted upon by a 1 pound force. So I can say that 1 slug equals 1 pound, 1 pound equals 1 slug times 1 foot per second squared. We also have the pound mass. Pound mass is the mass that's accelerated by 32.2 feet per second squared when acted upon by a 1 pound force. So 1 pound equals 1 pound mass times 32.2. So those are the units that we use when dealing with Newton's second law and kinetics. Now that we know the relationship between Newton's second law and motion, we can find the equations of motion. The equations of motion are simply those equations that relate forces acting on a particle to its motion. And as I mentioned, they're all based on Newton's second law. That is, the total force equals the mass times acceleration. Okay. Now we note that this is a vector relationship. Right? The force is a vector, it has magnitude and direction. The acceleration is a vector. The mass is a scalar. Since it's in vector relationship, as we saw in kinematics before, we can take advantage of the components of the vectors to decompose the forces and acceleration if necessary, and to solve those individual components separately. For example, in rectangular components, we know that the total force is equal to the mass times its acceleration. Decomposing that into rectangular components, the force will be the component in x times I plus component in y times j plus the component in z times k. That's the total force, or the components of the total force in rectangular components. That will be equal to the mass times acceleration in x plus acceleration in y plus the acceleration in z. And remember, each of those directions are independent, so we could look at those as three independent scalar equations. So in order for this to be true, it must be true that the component of the force in the x direction must equal the mass times acceleration in x. And it must also be true that the y component equals mass times acceleration in y, and the force in z equals the mass times acceleration in z. So these three equations represent the equations of motion in rectangular components. And each of these must be satisfied independently. So if you tell me the force, the vector acting on a particle, and the mass, I can decompose it into its components, and knowing each of those components and the mass, I can find the accelerations in each of the three directions. And from those accelerations, I can tell you the velocity in each direction and the position in each direction, given appropriate initial condition information. For example, if we have a projectile, here's a ball flying through space with nothing acting on it except the gravitational force. Then I can draw what's called a free body diagram, which consists of the particle of interest removed from any environmental surroundings, replacing those environmental effects with forces. For the case of projectile motion, my free body diagram, the only force acting on it is the weight. And if I wanted to add my coordinate system, I could do it like that, with z coming out. So that means the total force is equal to the weight. So from Newton's second law, the force equals mass times acceleration. The total force is equal to the weight, which must equal the mass times acceleration. Decomposing that into components, the weight acts entirely in the y direction. So the x component of the force is 0, the y is minus g, or excuse me, minus w, the weight, times j, and plus 0k. That has to be equal to the mass times the acceleration. So looking at the individual components, the equations of motion, in the x direction the force is 0 equals mass times acceleration in x. In the y direction we have minus w equals mass times acceleration in y. And in the z direction, 0 equals the mass times acceleration in z. So we see that in the x and z direction the acceleration will be 0, in the y direction the acceleration will be the weight over the mass. And that leads us to the weight, or the acceleration, excuse me, ay is equal to minus the weight over the mass. And now that we know that, we can solve for the rest of the motion like we did for ballistic motion as we saw before. A couple of notes about these types of problems. If your problem involves more than one particle, you have to write the equations of motion, separate equations of motion for each particle. So you have one application of Newton's law for each particle in the problem. And it's worth mentioning again the coordinate system from which you measure acceleration must be Newtonian, not accelerating in any way, changing orientation, or accelerating in a translational form. Just like with kinematics, sometimes in kinetics it's convenient to use tangential and normal components instead of rectangular components. So suppose we have a particle following a path, and there's some force acting upon it, like that. We know that the tangential direction is tangent to the path in the same direction as velocity, and the normal unit vector is perpendicular to that and pointing towards the center of curvature. So we can find the components of that force vector in these two directions. So this is the tangential force component, here is the normal force component. And we can decompose Newton's second law in tangential and normal components. So Newton's second law still looks the same in the beginning. Now we just describe the vectors in a slightly different coordinate system. So the tangential force has to equal the mass times the acceleration in the tangential direction. But we also happen to know that the tangential acceleration is dv dt. So the equation of motion in the tangential direction looks like that. And in the normal direction, the force in the normal direction has to equal the mass times acceleration in the normal direction, and that will be the mass times v squared over rho. So those are the equations of motion in normal and tangential components. Sometimes it's convenient to work in that direction. Dynamic equilibrium is a concept the book introduces. I'm not a huge fan of this concept, but sometimes it helps people understand what's going on, especially when relating it to statics, if you've had a statics class recently. So Newton's second law is just that the force equals the mass times the acceleration. I can rearrange that to say that the force minus mass times acceleration equals 0. This is the expression of dynamic equilibrium. If we consider the mass times acceleration term to be another force, they call it an inertial force, then we can treat our particle as if it's in static equilibrium. So it's in static equilibrium except that we have this extra force that is the inertial force minus mass times acceleration. And then you can solve the vector relations and problems just like you did when you were taking statics class. Just remember to include the inertial force. Now when we're solving equation of motion type problems, there are certain steps that we have to take every single time. Just like before, the 0th step is going to be to establish your coordinate system. Pick your origin, your positive direction for x, y, and z, normal, tangential, whatever component system you're going to be using. That's the very first thing you have to do. Same as with kinematics problems. Step 1 in these types of problems every single time is to draw a free body diagram. You probably did these in statics. You're just going to have to continue. They're even more important now, if not equally important. Something about this. you have to draw one for each particle. If there's more than one particle involved in the problem, each particle has its own free body diagram. More on free body diagrams in just a moment. You may want to sketch components as well in your free body diagram. That is, show the decomposed forces and possibly even include the acceleration vector. Okay, once you've got the coordinate system and you have your free body diagram, which is a vector representation of all the forces, the next step is to write the equations of motion. And decompose them into components. If it's rectangular, then you've got the force in x is mass times acceleration in x. Similarly for y and z. And then the final step is to find what those components are or perform any algebra necessary and solve for the accelerations. And then, depending on the problem, you may need to find velocities and positions, determining motion that way, or take other steps. But the important things here are coordinate system and free body diagrams prior to the writing of your equations of motion. Well, let's talk a little bit about free body diagrams quickly. FBD, free body diagram. Remember that a free body diagram is you take the particle of interest and you detach it from its environment, remove it from the environment, replacing its interactions with the environment by vector forces. For example, if you have a block resting on the ground, maybe this block has a mass, okay? Then the free body diagram of that, there's my body away from the environment, but replacing the environment with the forces. So in this situation, the force is acting on it. First, the ground is pushing up. We call that a reaction force, just holding it in place. So it's pushing up. I'll call it capital R for the reaction force. I also have the weight acting on this, and it's acting in a downward direction. So that's a free body diagram for this situation. Another example, suppose I have a block resting on a slope. Maybe this block is moving, maybe it isn't. Free body diagram of this will look as follows. First of all, I still have the weight and it still acts in the downward direction like that. At this interface, more on this in a moment, there's going to be a force parallel to the surface due to friction. I'll just call that F. And then there's going to be a force perpendicular. It's the same as the reaction force we had before. Call that R, the reaction force. And there's a free body diagram for that case. One final situation. Suppose I have a ball of mass M hanging from a string. It may or may not be moving. A free body diagram there. I take the string out, remove everything, and I replace those with vectors. There's gravity, the gravitational force acting on this, so there's the gravitational force, and also affecting this motion is the tension in the string acting along the string. So there are a few simple cases of free body diagrams. We'll see more examples in class. If we have a body in contact with the surface, it will definitely experience a normal force, that is a force normal to the surface. That's the reaction between the surface and the particle. For example, a car sitting on the ground. The ground is pushing up on the car, holding it up, if you will. That's the normal force. It also may experience a force parallel to the ground due to friction, or parallel to the surface. Okay? So the interaction of this particle with a surface, we always decompose it into the friction and normal components. Friction is always going to be parallel to the surface, and the normal component is always going to be perpendicular to the surface. So suppose we have a slope like this, and there's a block on it. And maybe this block of mass m is sliding down the surface, maybe it's sitting still. To draw the free body diagram of that, like we did before, here's my mass. I've got the weight acting on it downward. There's the normal force, which is perpendicular to the surface, so I know its direction. And then there's the friction force, which I will call F, and it's parallel, so I know its direction as well. The relationship force F is equal to, it's proportional to the normal force, and it's proportional through a constant called mu. Mu is the coefficient of friction. Mu can take two forms. There's mu sub s, which is the static coefficient, and mu sub k, which is kinetic. The difference between these two is that when there is no velocity between the particle and the surface, otherwise they're sitting still relative to each other, no slipping, then static coefficient of friction applies. When there's sliding between the two, then the kinetic coefficient of friction applies. Sometimes those coefficients, sometimes that friction can be very different depending on whether it's sliding or not sliding. Now I'm going to introduce the concept of angular momentum. Suppose we have a particle moving through space. Here's our coordinate system. And our particle has a linear momentum m times v, like that. And it has a position of r. We can take the moment of that linear momentum suppose we call the origin O. And this moment is called the angular momentum. So it's written as follows. H is the angular momentum, and we subscript it with the origin about which we're taking the moment. So it's the angular momentum about point O, and that's equal to the position of the particle in the reference frame, or with respect to O, crossed with the linear momentum. So the angular momentum is just the moment of the momentum. Now, as a consequence of, so I could also draw the angular momentum, if you'd like, vector, h sub O, like that. As a consequence of the cross product itself, the angular momentum vector will be perpendicular to the plane defined by r and mv. So those two vectors, r and mv, will define a plane, and h naught is going to be perpendicular to that. The units of angular momentum are either kilogram meters squared per second or foot pound seconds. Now, you may recall the definition of the cross product, and it's worth reviewing the cross product and its definitions, particularly regarding angular momentum. But just to rewrite the equation, we're crossing the position vector r with the linear momentum. If looking at the components, r will be x, y, and z. Sorry, that's a j. The rectangular components of the position vector, the rectangular components of the linear momentum vector will be mvx. Now we can write the angular momentum then is defined. This cross product can be written as the determinant of a vector, a matrix, whose first row are the unit vectors, I, j, k, in the components that you're working. The second row are the components of the first vector in a cross product, so that's r. So the components are x, y, and z. And the third row are the components of the second vector, mvx, mvy, mvz. So the cross product is the determinant of this matrix. And I can write that out, the result out for you. That will be, for this vector, it will be equal to the following. And the result of this cross product looks like the following. Writing out just the components of that angular, three-dimensional angular momentum vector. The component of the angular momentum vector pointing in the x direction is m y vz minus z vy. And in the y direction, now, so that's for the full three-dimensional. We will rarely do the full three-dimensional problem. You do need to be able to do the cross product. So review these relationships and how you do those. Frequently, we will talk about a particle moving just in a plane. So planar motion. If we're just in the xy plane, that means that z and z dot are always equal to 0. So as you can see in this one, z is 0, vz is going to be 0 as well. I should write that explicitly, vz. So the component in the x direction is 0, similarly in y. The only thing that's left is in the z direction, and so the angular momentum for a particle moving in the xy plane is just the mass times xvy minus yvx. So it reduces quite a bit. Another way of doing two-dimensional angular momentum is to write them in polar coordinates. We use polar coordinates frequently when we talk, and angular momentum together, when we talk about satellite motion, so something orbiting the Earth or the Earth orbiting the Sun, something like that. So in this case, if we have a particle and it has some linear momentum mv and a position r, like that, let me define this angle as phi. If that's the case, and again to highlight, this is two-dimensional polar coordinates, then the angular momentum will be equal to rmv times the sine of the angle phi. So just as a little aside, if I have a vector A and a vector B like that, and this angle is phi, then A cross B, right, the magnitude of that will be equal to AB sine phi. That's just a math relationship from cross products, okay? And I think you'll notice that this component, the way we've drawn it here, mv times the sine of phi is just equal to the component of the velocity in the transverse direction. Okay, so that means that the angular momentum is equal in 2 dimensions is r m v theta. That's from radial transverse components. But from radial and transverse components, v theta is also equal to r times theta dot. So the angular momentum is equal to m r squared theta dot. And that's the relationship we're after for angular momentum in 2-dimensional polar coordinates. Now let's look at the derivative of the angular momentum. Remember, it's defined as r cross mv. Okay, so the time rate of change of h naught, which is h naught dot, is equal to, so we have the derivative of first cross with the second plus the first cross with the derivative of the second. It's sort of a chain rule thing, but we have to maintain the order. So this is dr dt cross with mv plus r cross with dmv dt. So this is equal to dr dt is the velocity, so it's v cross mv plus r cross with, assuming the mass is constant, it's m times the derivative velocity, which is the acceleration. Okay. Now, this term is always going to be 0 because v and mv are collinear. They point in the same direction. So their cross product will be 0. So all that's left is that the time rate of change of the angular momentum is r cross ma. Now I want to take the moment of Newton's second law. Newton's second law is the force equals mass times acceleration. So the moment of that is r cross with the force and r cross with ma. Well, r cross with the force is just the total moment. So that's the moment about O, right? And r cross ma, as we just saw a moment ago, is the time rate of change of angular momentum. So we have a new equation that is the total moment equals the time rate of change of the angular momentum. This is sort of a rotational Newton's second law. And it's another source of equations of motion. We can treat this the same way we did Newton's second law. Split the vectors into components, solve for the acceleration or the angular acceleration, things like that, and decompose our motion that way. Backing up a little, we can also decompose Newton's second law. Before we did it in rectangular coordinates, we did it in normal and tangential components. We can also decompose Newton's second law in terms of radial and transverse components. So if I have a particle at position r theta, so polar coordinates describing its position, and it's traveling along some path, and now I have a net force acting on it. I can decompose that force into the radial component and the transverse component. Like that. So, if the total force is mass times acceleration, still Newton's second law, in components, I'll have the radial force equals the mass times the acceleration in the radial direction, and the transverse force is the mass times the acceleration in the transverse direction. But we previously defined radial and transverse acceleration, so that this will be equal to the mass times r double dot minus r theta dot squared. That's the radial direction, and in the transverse direction, r theta double dot plus 2 r dot theta dot. So we can decompose our equations of motion in radial and transverse components, solve for those separately, and then determine the motion. We now look at the special case of motion under a constant force. If particle is moving along a path, here's our particle, it has some momentum m times v. And if the force that's acting on it is central, and that is its line of action is through the origin, so since that line of action is moving through the origin, that means that the moment of that force, r cross f, has to be equal to 0. Since the force acts through the point about which we're taking the moment itself is 0. Well, as we saw before, the moment is equal to the time rate of change of the angular momentum, right? Since the moment is 0, the time rate of change of angular momentum also must be 0. And that's true for all time. So what that implies, if the derivative of something is 0, that means the something must be a constant. So that means the angular momentum is equal to a constant. Or we say angular momentum is conserved. Furthermore, well, so the angular momentum is conserved, or the angular momentum is equal to a constant. This situation occurs, for example, if we have a satellite orbiting about a planet, or the sun orbiting about the sun. The force acting on them acts between their two centers, right? The attractive gravitational force. And so if you put an origin at the center, this force becomes a central force. And so the angular momentum of the satellite must be conserved. Well, we saw a moment ago that the angular momentum magnitude, since it's conserved, this has to be a constant. Also, the direction is a constant. Since the vector is a constant, its magnitude is constant, and its direction is constant. Remember that the angular momentum is equal to r mv sine phi in that previous depiction. And so this must be equal to r naught m v naught sine of phi naught, where this is some initial condition. So if I tell you where the satellite is at some particular point in its orbit, you can infer information about the velocity and distance from the center at some other point. And as I mentioned, this equation is used a lot when we talk about orbital mechanics. Newton's law of gravitation is also useful in orbital mechanics. It says that the gravitational or attractive force between two bodies is equal to, F is equal to G, the gravitational constant, times 1 of the masses times the second mass divided by r squared. Now a little bit about the notation. G, the gravitational constant, that's G in both of our unit systems. M and the big M and little m, those are the two masses, maybe the mass of the Earth and the mass of a satellite, the mass of the Earth and the mass of the Sun, whatever two objects you're interested in. And R is the distance between the two masses' centers. And that's important, the distance between the centers. If you talk about a satellite rotating about the Earth, it's not the distance from the satellite to the surface of the Earth, it's the distance from the satellite to the center of the Earth. And one final thing about if you're interested in a particular planet, capital G, the gravitation constant, times the mass of that planet, maybe it's the Earth, is equal to the gravitational constant times the radius of the planet squared. So if it's Earth, this is 32.2 feet per second squared or whatever.